everybody, this is Dan, aka Entertainmentwf. Now, today, since it's the holiday season, I felt like talking about a little bit more of a mathematical topic that can apply to all my Mega Man fans out there, or anybody that's interested in making fan games that relate to the topic we're going to talk about, or just how do you do this kind of thing. In terms of what we're going to talk about, we're going to be talking about lattice crypto systems, i.e. we're going to be talking about using some matrices, and we're going to be calling this the lattice Mega Man crypto system, just for the sake of that. This is very evident and seen in the Mega Man series, and the classic ones especially. Anyway, when we're talking about this password system, we're talking about the kind that you see in like Mega Man 2, Mega Man 3, Mega Man 4, Mega Man 5, Mega Man 6, Mega Man 7. It relates to coloring or selecting some numeric system and returning to your game based on some status, i.e. you're given some password and you want to return to the game. How do you implement something like this? Or even how do you interpret it? How secure does your system need to be? Well, you need the system so that you can't guess your resuming state, so that you can just resume your game when you know the password rather than guessing it by exhausting all the possibilities. Which is the balance between getting a good Mega Man password system versus a bad one. A good one should be easy to input, but very difficult to crack i.e. by just exhausting it, by just going plop, 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 plopping out different points and exhausting them, which can be easy in some situations, but we're going to look at that and see how bad it can get or how good it can get. Anyway, let's get to our definitions here, because this is accurate to what you would see in any Mega Man game, but it can apply to other password systems. I'm just talking about this in this sense, since it's easy to visualize. Anyway, I apologize if there's this glare over here that makes it very difficult to see what's going on over here, and I promise this text is going to, what I'm going to write down is a little bit bigger than this. This is just the introductory definitions. Anyway, we're going to call this a lattice Mega Man crypto system. Now, we're going to say there's a constraint lambda that's a positive integer, i.e. 1, 2, 3, 4, 5, all the way on to some large finite number. Lambda will be the constraining value, because you don't want to be able to just... You could just think of this, how many dots can you put in that grid that you see in the password screen? I.e. it could be red dots, blue dots, I don't care, as long as it's just the count of how many of them there are. And the case where you just have the number of them is just where lambda is equal to n times n, where n is the dimension of one of the vertical or horizontal lattices. I.e. if you say have a 3 by 3 square, you have 9 squares that you can put these dots inside of. But we're going to refer to that as the variable m in this semi-lecture, I guess. And we're going to say a key k in the LMM, which is the lattice Mega Man crypto system. We'll just refer to that as LMM. Just for now, unless I ever refer to it, is an n-ary string which accepts when a valid key system k exists, so that the string k is inside of the key space, the valid key system space. I.e., if you give me some string, like, if you don't know what a string is just a sequence of symbols that are concatenated together. And this you can just think of as just say your square, and we'll be talking about how you get it out of the square and put it into the string and then send back. Anyway, so we're just saying, okay, we have some sequence of symbols. You can just think of these like alphabetical symbols, you can think of them as numeric symbols, anything. As long as it fits in some language. At least that you can define, that can be constructed in a computational sense. But we're just going to refer to a string as a sequence of symbols. Just for that, nice and simple. Okay, so if this string of symbols, like the sequence of symbols that are all stringed together, called a string, k is inside of the valid keys, like i.e. your password that is a valid one, it'll resume the state based on whatever you gave it. So if it finds the match, it'll resume to the state that it's instructed to. So you can think of it like, say if we're talking about Mega Man 3, say you beat Needle Man, for instance. And Needle Man is the guy that you want to return from a state. Like, say if you got a game over and you got super annoyed by Shadow Man stage for some reason because that lava part right at the beginning. Say you just like, oh, I beat Needle Man, but I want to get back there. So you put in the password, like with those dots, and you just say, okay, I want to continue. And this string is developed from the sequence of dots, and it compares it against the game's cartridge data on the passwords, and it says, okay, you beat Needle Man. Okay, continue. Okay, that's basically what we're going to do in a nutshell. That's the mechanism. But there's different ways of doing this. Okay, now back to our definition. Okay, now K, the string of symbols, can contain at most lambda non-zero entries. Now what does that mean? That means that, okay, there should be like a positive integer number of these symbols that are not zero, i.e. blank spaces. So you can think of it like on your grid, you're only allowed to have lambda of them. This is some constraint we're going to put on this. Because you don't want to be able to get the guy the plop and everything, because it might make things very difficult to implement, and it might make things a little bit more space constrained. Like I'll show you exactly what I mean later on when we're talking about the possibilities on the spaces, and when you have a possible key versus ones that you should have. And we'll see what exactly this all means. But right now we're just going to be talking about, okay, so say we have a string with 5 like, okay, well, say we have a 3x3 string. Say it'll be just the non-zero entries are the ones that don't pop out dots. So, like, no, the non-zero entries are the ones with dots inside of them. Say your grid there. We'll do an example after. Okay, so this potential string is a W, and it's a sequence of symbols, like we were talking about the strings, from x0 to x m times m times m minus 1. So you can think of m times m is your grid, and since we're starting our indexing from 0, we're going to go to the 1 just before the count. And yes, I know the glare kind of goes down as soon as I take my hand away from there. It's like this is the flaming zone. Anyway, so now how do you interpret one of these strings from the grid? What you do is you follow the string, like you can think of this like your dots. We're going to map symbols to dots. Okay, so your string, when you're interpreting it, will be reading it from, this is the first symbol, second symbol, third symbol, fourth symbol. Then you go down to the second row, and you go into the zigzag linear string pattern. So for instance, a basic example would be the case where we're talking about a square here. And can you see that? Okay, good, you can see that. Okay, say if I have a dot here, let me get a better marker here. Better markers. Okay, so the blue dot is the same as this red dot's going to be. Okay, and we're just going to assume that there's only one coloring. So i.e., we'll talk about the definition of colorings, and we'll say, okay, there's a red dot, and here's another red dot. Say we're only allowed to have a maximum of 4 symbols. Okay, so when we write out this string, we'll say every single time there is a dot, dot is the same as 1, and a blank space is 0. So we'll say the string above is equivalent to saying, 1, 1, 0, 1, 1, 1, 0, 0, 0, and then lastly there should be a 0, 1, 0. And as you can see here, the 1 corresponds with the 1, 1, 1, 1, 1, 0, 0, 0, 0, 1, 0. And now what you could do is you could just place this inside of an array. You can actually think of these strings just as character arrays. Or you just think of it just as a normal array. And you can just transcribe between your drawing events and strictly towards the string here. And you can use those for comparisons, and you can get actually some really good algorithms for string comparisons, which like the, I think it's, KMP, sorry. KMP is the algorithm. I totally had a brain fart there. Anyway, now we're going to talk about, okay, so this is how you interpret it. Like we just did in this example, use the zigzag fashion. And now, when you go about this, you're going to say, okay, I have this new zigzag pattern, and I know how to interpret these dots, but how many dots can I have, and how many of these things can be colored? Now this is a new problem, not just a strict 1-0 binary problem, which you can represent actually in a nice efficient way with hex. Although you can do this with the other coloring systems, but that's a matter of efficiency. This isn't a big problem, but you can think of it like, say, if we were doing this back in the old days, you'd be doing this as hex digits more than likely, and then you'd be doing a lot of bit shifting. But okay, now we can talk about this in multiple different ways. I'm not saying that these are the only two ways of doing this. I'm just saying that these are probably the most two convenient ways of doing this and make the most sense. And probably this is how it's really done. Like, at least in the games that you've seen. But theoretically, this would probably be the better of the two options. Okay, say if you want to have low space constraints. Say you know how many codes you want, and you want to make it so that it's nice and efficient for you to code up these things, because these codes will require hand coding them. They aren't a mathematical principle here. You can make a mathematical, like, generating functions, but it won't be that. It's best to make codes more, since we're dealing with codes, not say a crypto system that is strictly based on some sort of mathematical principle. These are still dealt with mathematical principles. It's nice and simple. It's just a matrix of m times m. It's m and n, m by n. Sorry. Okay, so there's going to be two that we're going to talk about here: singular and cumulative. And okay, a singular system, I'm just defining it this way. A singular system is a system where we're going to assign special lattice points for particular unique events. Like, say, if I was in our example here, say this guy right here. This guy right here indicates that you beat Needleman. You beat Needleman. This indicates that you beat Needleman. This guy consists of, like, so say if you put a dot there, or if you didn't put a dot there, that represents some sort of event. Say this beats Shadow Man. This represents beat Shadow Man. And then what you do is you just assign lambda to the number of events that you want or not even want. You can actually still just make lambda any constant here, and it'll represent these symbols here. Because you could just say, like, okay, a blank space here means that say you beat we beat Hardman. So say you beat Hardman. Okay, that's how a singular system is going to work. You're going to just assign lattice points to represent particular events. And we're going to talk about the security of this and other things dealing with the relation with lambda. And then, now the second system here is called cumulative. Cumulative means that each specific event has its own special code. Instead of assigning events to particular lattice points, i.e. different entries on this matrix here, we're going to speak of that as a lattice point, just for if anybody's confused to what I'm meaning with a lattice point. We're going to be talking about cumulative being that... Wait a second, I confused my definition, sorry. Singular means that each one of these has a unique code, and cumulative means that each one of these is an affiliated event. I apologize. So, just for sake of definitions, whenever I'm referring to a cumulative system, remember that each one of these lattice points is a significant event. So, I apologize for the confusion there. So it's actually the singulars we're going to be talking about right now. Okay, a singular event is involving, say, if we take one code here, and we're going to say, okay, this one unique code means that Needleman was defeated. And say I have another code. The code says, okay, Needleman and Shadowman were defeated. And say you could think of this as different codes for different representations. But now this comes into the account of number of events that you have. Say, how many Robot Masters? How many stages do we even have in the game? Now this comes into the question. And now we're going to be referring to this as our problem with setting up this crypto system. And now this is the next portion of our discussion.